In that warm-up exercise, we found a function to which a power series converges over its domain, its interval of convergence. What we actually want to do, though, is the reverse of that process. We start with a function and we try to find a power series to represent that thing. How do we do that? Well, I'm glad you asked. We can start with a geometric series and manipulate it in some kind of way. We kind of saw a preview of that again in that warm-up exercise. Or maybe we already have a series that we're familiar with and we can do some algebraic manipulation on that thing on some kind of known series. And that algebraic manipulation could be adding terms, subtracting terms, multiplying, or maybe even composition, something like that. And we can also do some calculus, like term by term differentiation or integration in order to get the power series that we seek. Here, let's look at another example. Find a power series representation of f of x is equal to 1 over 1 plus x. So recognize this as this sort of looks like that geometric sum. Sure, there's a plus sign there instead of a minus sign, but you know what? We can totally fix that. Why did this thing restart? I don't know. Is it going to pick up where we left off? Looks like it did. Sorta. All right. So I think I got enough space to do this. We want this thing to look like S is equal to A, first term, over 1 minus R. Well, we're good in the A department, we're good in the 1 department, but not the R department because it needs to be a minus R. So I'm going to do some mathematical trickery here to make this look like 1 over 1 minus, beep, negative R. And there you have it. We have an A value. We're going to go with green here. An A value of 1. We're starting here with a 1. And our common ratio is going to be the thing that's in parentheses. It's a negative x. All right. So if I'm going to represent this thing as a power series, this should be equal to the sum from n equals 0 to infinity of, our first term is 1, don't really need to write it down, times our common ratio of negative x raised to the nth power. And then maybe I do a little bit more manipulation on this, thinking of this inside here as a negative 1, right here. I'll actually even write it, a negative 1 times that. And then I'll use a property of exponents to multiply each one of these to that power, or raise each one of these to the power. So it's negative 1 to the nth. Oh, look at that. It's alternating. And then x to the nth power. So let's say, for example, we wanted to expand out this series here as a power series, this infinitely long polynomial. What would happen if we stuck in 0 here? If I stick in 0, this goes to 1, and that also goes to 1, so it's 1. Hey, but we knew that already because our first term is equal to 1. Right? Okay. If I were to stick in 1, that'll be negative 1 to the first power, so it's going to be negative, and then x to the first power. But also, we knew that because our common ratio is negative x, so we could just multiply 1 times negative x and get negative x. I can multiply negative x times negative x, common ratio, and get positive x squared. And then the next term is going to be negative x to the third, because we multiply by negative x, dot, 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 plus, and then our nth term here is a negative 1 to the nth times x to the nth, but then it just keeps on going. All right, so there's how we represent a function as a power series. But, you know, again, this was one that seemed like we could make this formula fit. Maybe one more thing that I might do for this is I might try to figure out what the interval of convergence is. Well, the interval of convergence is just basically, let's see, I use the ratio test, the limit as m. N goes to infinity, absolute value of the n plus 1th term, negative 1 to the n plus 1, x to the n plus 1 over negative 1 to the nth, x to the nth. Hey, since this is absolute value and the negative 1 to the n plus 1 stuff all of that stuff is just going to be either a positive or negative 1. It's going to go away. Subtract our two exponents, and we get, this is equal to just x to the first power. And we need an absolute value around it because who knows what we get to stick in there. And then by the ratio test, that must be less than 1. And we still get negative 1 is less than x, which is less than positive 1. Huh. Well, we probably could have gotten that since it's thinking of it as geometric, as just this negative 1 crammed in there, and that negative 1, the negative part would go away because of the absolute value, and we would have still gotten that thing as its interval of convergence. Here, let's take a look at another one. Okay, well, that was about to reveal some answers. Find a power series for f of x is equal to 4 over x plus 2. All right, so we're going to do the same thing. We're going to treat it as if it's geometric and then see if we can make it fit this formula. S is equal to a over 1 minus r. If you learn nothing else, if you get nothing else from this lesson, maybe us saying this so many times will burn it into your brain so that you never even have to think about it on the AP exam. It's just automatic. Anyway, this does not look like that. It looks so far like our A value is going to be a 4, but then, well, we can't really say that because we have stuff in the wrong place down here at the bottom. All right, so let's just try to do some manipulation on this. I got 4 over, I'm going to switch the order because it needs to be the constant value here and then the variable part. Okay, first step though, that thing there has to be the number 1. How can I get this to be the number 1? Well, if I divide everything by 2, I can make that thing the number 1. Divide by 2, and divide this one by 2 as well. So now this becomes a 2 on top, 1 plus x over 2. All right, so we have our 1 there. We're in business. But now this needs to be a minus a ratio, a minus the common ratio. So we'll do exactly what we did on the previous couple of x, no, just the previous one, and make that minus a negative. 2 over 1 minus, boop, negative x over 2. And there we have it. So we've now successfully turned our regular function here into a geometric sum. So now it should be pretty easy to write the power series for this thing. Our first term here is the number 2 right up top. And our common ratio this time is going to be a negative x over 2. So writing this thing as a series, that'd be summation from n is equal to 0 to infinity of, our first term is 2, and then our common ratio is negative x over 2 to the nth power. Now I might clean this thing up, do a little bit of algebra on this, give this n to each of these things down inside of the parentheses, and then also do the same thing that we did with the negative sign here, make that a negative 1 to the nth, which I just erased. Here, I need to dial that back. Go back in time. All right, so summation 2, I'm going to make that a negative 1 to the nth, and then I'm also going to have x to the nth and 2 to the nth, which, you can kind of leave it like that. But if you want to, since we have a 2 here and we have a 2 down here in the denominator, think of it like this. I've got a 2 over a 2 to the nth power. This is 2 to the first power. And we would subtract our 2 exponents. I want to keep this one down here because I don't want a negative n. So I'll subtract this 1 down here on the bottom to make this 1 over 2 to the n minus 1. All right, so then here, finally, summation n equals 0, infinity of negative 1, alternator, x to the nth over 2 to the n minus 1. There is our power series. Let's say I wanted to expand this thing out as a function. So this f of x is equal to, what's our first term, I wonder? I think it's 2. And then to get all the rest of the terms, all I have to do is multiply by this common ratio. So if I multiply 2 times negative x over 2, the 2's will cancel. I'm just left with a negative x. So there's the next term. Of course, I could have gotten both of these terms. If I plug in a 0 in here, You know what I forgot? Nobody shouted it out. I forgot the N on this one. But I caught it. Anyway, if I plug in a 0 here, I would have gotten this 2. If I would have plugged in a 1 here, I would have gotten a negative x. And then finally, let's just keep going here. If I multiply this term by a negative x over 2, the negative times negative makes a positive, x squared over 2. Let's do maybe one more, minus, because I'm going to multiply by negative, and x cubed over 4 plus dot, 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 plus, I'm running out of room, so I'll just move this thing over. Our nth term, negative 1 to the nth power, times x to the nth over 2 to the n minus 1 power, and then it's got to keep going. All right, now then, this original function, though, has a domain of x is just not equal to negative 2. However, that's not true of this thing as a power series. It doesn't have necessarily that same exact domain. How do you find it? You find it with a ratio test. But here, I don't even have to do the ratio test because this was gotten from a geometric series, which means that all you have to do is take the common ratio here, bloop, 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 and make that thing, common ratio, negative x over 2, and make that less than 1. You can get rid of that negative sign because it is absolute value. Boop. And then, let's see, that 2 is already positive, so we can bring that outside. We got absolute value of x over 2 is less than 1. You can multiply the 2 over, and that becomes the radius of convergence. And then cram this thing in between a positive and a negative 2. So negative 2 is less than x, which is less than 2. So here is the radius of convergence for this function represented as a power series. And we can see definitely doesn't have exactly the same domain. We are kind of starting at this asymptote, or just to one side of it, just to the, let's say to the right side, but we only get to go up to the number 2 and then no further, because anything beyond this series would diverge. Okay, and hey, wait, don't we have to check the endpoints? Nah, man. And the reason why is because this is geometric, and for geometric ones, the test, like a geometric series, does not converge when your common ratio is equal to 1. It only converges when it is greater than 1, so we don't have to do that part of it. All right, I got a little bit more on this. So here's the animation for all of this stuff. It looks super sweet. I'm pretty sure we did all of this stuff. Let's check to see if I got it right. PowerPoint's going to tell us. All right, so far so good, right? And then here's what our power series looks like. Wow, okay, yeah, we got all of this stuff right too. Oh, it went one extra term. Okay, it's whatever. So it's saying that this rational function is equal to this power series here, but only over this interval, all right? And then multiply both sides by that 2 there. And that's the interval of convergence. It's the domain over which this thing, power series, converges to this rational function. And this rational function represents the sum of the series for whatever x value we choose to put in it. All right, a couple more things here. Doesn't this thing right here mean division? You got 4 divided by x plus 2. So let's do a little bit of long division on it. So long division, x plus 2 goes outside of the house and 4 goes inside of the house. It would look like this. And notice that when you do the polynomial long division, you get the same exact series that we got, by that long tedious method that we just used. So here's how this division would play out. I want to know, hey, what do I have to multiply 2 by to get 4? And I would have to multiply that by 2. So multiply the 2 times both of these things. I get a 4 plus 2x. Oh man, I get this 4x is like this part this 2x that's left over. But that's okay. I can subtract both of these. So when I subtract, those are gone. It brings down a negative x. Let's go ahead and let's see, how many times does 2 go into negative 2x? It would go in there negative x times, so take negative x and multiply it times both of these, and you get a negative 2x minus x squared. Subtract these, change the signs, you get x squared. Well, you can see it. It's going to go on forever, right? So essentially, Like the stuff that you did in Algebra 2 kind of led us to this. It's just that we never ever kept going with this. We would have just taken the remainder, whatever was left over, and we would have put that over, let's say, whatever your divisor was, and been done with it. But here, this is kind of like when you first learned to divide back in, long division in fifth grade, you had the R2, R3 for your remainder, right? That's what you did in Algebra 2. But now, this is like the decimal expansion of that. Like we're just going to just keep on going and keep on going, regardless of the fact that those decimals go on forever.